Hi, this is Alex from devstories.eu. NumPy, Episode 2 of 7. You rarely type out data by hand in data science. Instead, you need to summon vast empty grids and numerical ranges into existence with a single command. Let us talk about the intrinsic functions that let you create arrays from scratch and control their structure. First, a quick correction on manual creation. When you convert a standard Python list into an array using the basic array function, a common mistake is passing multiple separate arguments to create multiple dimensions. The function expects a single sequence. To make it two-dimensional array, you pass one list that contains other lists, not two separate lists. Every array you create carries structural metadata. Two properties matter most here. The first is ndim, which tells you the number of axes or dimensions the array has. A flat sequence has an ndim of 1, while a flat grid has an ndim of 2. The second property is shape. Shape is a tuple of integers indicating the exact size of the array along each dimension. If you have a matrix with 2 rows and 3 columns, its shape is 2 by 3. The length of the shape tuple will always equal the ndim value. Creating arrays from existing lists is fine for small tests, but real work requires generating arrays programmatically. If you need a placeholder to fill with data later, you use the zeros or ones functions. You simply pass a shape tuple to these functions and they return an array of that exact structure, populated entirely with zeros or ones. By default, these functions create floating point numbers, but you can override this by specifying a different data type. When you need a sequence of numbers, NumPy provides two main tools. The first is arange, which works much like standard Python range. You give it a starting value, a stopping value, and a step size. It generates an array of numbers spaced by that step. While arange is great for integers, using it with floating point steps can cause unpredictable results because of how computers handle decimal precision. The number of elements you get back might vary slightly depending on microscopic rounding errors. That brings us to linspace, which solves the floating point precision problem. Instead of defining the step size, you define the exact number of elements you want. You give linspace a start value, a stop value, and the total number of points. NumPy calculates the exact spacing for you. Consider a scenario where you're evaluating a mathematical function over a specific interval. You want to calculate the function across a smooth grid of coordinates between 0 and 1. Using linspace, you can generate exactly 100 evenly spaced coordinates across that interval. You get a perfectly distributed one-dimensional array, guaranteeing that both the start and end boundaries are included. This is where it gets interesting. The distinction between these two sequence generators dictates your workflow. Use arange when the exact step size matters, like counting integers by 2s, but always use linspace when dealing with floats and intervals, so you can guarantee exactly how many data points you get and precisely hit your boundaries. Appreciate you listening. Catch you next time.